Okay, this is a review of quiz on Chapter 3, Mendelian Genetics. Mendel's first postulate is genetic characters are controlled by unit factors existing in pairs in an individual. What is the modern term for unit factors? So the best answer to this is E, alleles. So the trick to this is the fact that the unit factors exist in pairs. So we have pairs of alleles. We have two copies, two alleles. We don't have two genes. So that's the reason that alleles is the best answer. Some of you found some textbook text that suggested that unit factors are genes. So I also gave you credit for that answer. But the best answer for this is alleles. Mendel's third postulate is during the formation of gametes, the paired unit factors separate or segregate randomly so that each gamete receives one or the other with equal likelihood. So when does this segregation occur? The answer to this is C in meiotic anaphase 1. So this is when the homologous chromosomes separate and each homologous chromosome has its own allele. And so the randomness of the order, the randomness of what a gamete contains is determined by what homologous chromosome it receives during meiosis 1. So meiotic anaphase 1 is the best answer for this. This question tests your understanding of vocabulary, so character, trait, and phenotype. And the answer is in the same order. So a character, whisker length is a character. So I haven't specified the variant. So I just say whisker length is something that can vary. So it can be long or short, but I don't specify what the variant is, so that's when it is a character. If I specify the variant, then it's a trait. So whether or not you have hair on your toes, that can be a character, but if I specify you have hairy toes, then that is a trait. And then a phenotype is a composite, so it can be more than one trait. And so here when I specify hairy toes and long whiskers, that's two different traits, and the composite of those together is the phenotype. Question number 4, in a cross between two individuals, B, little b, big G, big G, big B, little g, little g, what ratio of phenotypes would be expected in the offspring if the two genes show independent assortment? So the first thing I would do when I answer this question is I would calculate the number of gametes that each one of these individuals can produce. And so the answer is 2 for both of these. So both individuals can produce 2 different gametes. The first individual can create a B, G, or it can create a little b, big G. The second individual can either produce a big B, little g, or little b, little g. And so here we've just built the beginning of a Punnett square. So I can create a Punnett square. And so now we can actually draw out what we can see. So for this individual, so now I've just completed the Punnett square to show all the 4 possible genotypes that could be produced depending on the combination of gametes used. So I'm looking at the ratio of phenotypes that would be expected in the offspring if the 2 genes show independent assortment. So then I have to group these further. And so these and this. So these 3 genotypes should all share the same phenotype because we're assuming dominance recessive relationships here. So big B will be the same as big B, little b, and then these 3, and then they also share the same genotype for the big G, little g. This individual will have a different phenotype because he is homozygous for the recessive B alleles. And so the answer to this question should be D, 3-1. How many different gametes can be formed by the genotype? So we have heterozygotes for 3 gene. So the most straightforward way to do this is just to do 2 to the third, which is equal to 8. So 2 times 2 times 2 is equal to 8. So there's 8 total gametes that are produced. You could also potentially list all of them out, choosing all the combinations. Which of the following individuals breed true? So A and C, they're homozygous. They each produce 1 gamete, and that's the definition of breeding true. If A is dominant to little a, an individual with the genotype big A little a will have the same phenotype as this individual. That's just the definition of dominance. And now the pedigree, which I think is a little bit more challenging for many of you. So assume that blue individuals suffer from albinoism, a recessive autosomal disease. Further, assume that an unrelated individual who marries into this family is not a carrier. What possible genotype? So we're going to go through multiple questions on this pedigree. And so the first thing to do is just to note all of the individuals that you know with certainty what their genotype is. And so we know with certainty that this individual, we'll try. So we'll try opening that again. Oh. So we will simply write out all of the individuals that we know with certainty what their genotype is. So these are the easiest. It's recessive autosomal disease, so we'll just use little a to designate people that have albinoism. So individual 2-1 has albinoism, and individual 5-1. And so we know their genotype must be little a. Some individuals we also can mark because we have been told that individuals that marry into the family are not carriers. So we can also fill in, for example, this individual, this individual, this individual, and this individual, and this individual. So you might also wonder about 1-1 and 1-2. So we can't assume that those individuals don't have albinoism because we have evidence to the contrary. So this individual is little a, and so we know with certainty that both of these individuals are carriers. So we can also, for example, fill out these individuals. And so they both must be carriers because in order for an individual to have a homozygous recessive disease or trait, the parents either have to have that disease or trait, or they have to be carriers. And since these two individuals don't have albinoism, we know they must be carriers. And so we can do the same thing down here for these two individuals. So because individual 5-1 has albinoism, we know with certainty that they are carriers. And since this individual is a carrier, we know with certainty that this individual has to be a carrier, and this individual has to be a carrier. And then similarly right here, we know that this individual is a carrier, and so far so good. So individual 2-3 and 2-4, we don't know with certainty what their genotype is. And then finally, individual 3-1, we also don't know for certainty. Actually, we do know for certainty, We do know for certainty that this individual is also a carrier. And so the reason we know that is because one of the parents is homozygous dominant and one of the parents is homozygous recessive. And so each one of these individuals can only supply one type of gamete, and so the genotype of this individual is fixed. All right, so what possible genotypes can the individual 1-1 have? The answer to this question is, now, we've already worked it out, is big A, little a. So we have done this one. We've answered the question for this one. Using the above pedigree, which can describe the relationship between 4-1 and 4-2. So this person is the husband of this individual, and you can also say it's the cousin of this individual. So because these two individuals share great-grandparents, they're also related as cousins as well. So most properly, I think, I believe second cousins is the relationship. Assume that blue individuals, what is the probability that 3-6 is a carrier? So we go back up. I'm sorry, this was not properly filled out. So this individual did not marry in, so I think I actually accidentally filled this out earlier, looking at it as this person married in, but this person is actually related to this individual right here. So there's a 50% chance that this individual has albinoism. So this, we know that one of the two alleles is definitely going to be an A, big A. So the mother is definitely going to provide a big A, but the father is either going to provide a big A or a little a. So there's a 50% chance that this individual is a carrier. So the answer to this is 1/2. Now 3-5, and so 3-5 we knew with certainty was a carrier. So this answer is just 1. And then the final one is individual 2-3. So we go back up here, and we note that we haven't figured out what this individual is yet. So this individual has heterozygote parents for both, and so if we simply did a Punnett square, what we would find is that the Punnett square would be 1 AA, 2 AA, and 1 AA. So initially we might think that there's a 50% chance that this individual is a carrier. Is that the question? Is it a carrier? Is it a carrier? Yep. So initially we might think that this person has a 50% chance of being a carrier. However, this individual does not suffer from albinoism, so we know for certainty that they can't have that genotype. And so this is where renormalization comes into play. And so there's 2 possible ways that they can be a carrier, and there's 3 total genotypes that they can have. So the answer to this is simply 2/3. All right, so hopefully this has cleared up any confusion that you might have had on this chapter.